All right. Um, so, uh, right. So let's get started. I am recording. Yep, I am recording. So I'm just going to give one more important example of this whole energy diagram business, right? So here was one example of an energy diagram, the gravitational potential, another example of the spring potential. This was just some random practice example. I'm going to give the example of the Lennard-Jones potential. Now, you may have heard of the Lennard-Jones potential in chemistry because it does show up a lot there. This is the same thing. It's but it's very much on the border between physics and chemistry. Yeah, so everything today is up for grabs on the exam. Whether or not I'll actually put it on the exam is a different story. Right, so what we're going to try to do is we're going to try to draw a qualitative picture, or not a qualitative picture, draw an accurate picture of the Lennard-Jones potential given a qualitative description. I haven't decided yet. There's probably 4 or 5, maybe 3, definitely not 3 actually. So let me give some descriptions of the Lennard-Jones potential. So the Lennard-Jones potential is a potential energy associated with the force between two particles for which the force between them depends on the distance between them. That is, so this is a lot like gravity or electricity, well, which you guys haven't understood yet, but the point is it doesn't depend on the exact positions of the two particles, it just depends on how far away the two particles are from each other. So we can write the potential energy, U, as a function of just R, the distance between them. And what we can do is we can actually just pretend that one of the particles, by the way, when I say particles, think like atoms or molecules, that's what this describes. We can imagine that one of the particles is at the origin of our coordinate system. So then the other particle is somewhere else, and then the distance. So if one particle is at the origin, then we can easily compute R as just the square root of x squared plus y squared plus z squared, where the other particle is at x, y, and z. So far, the fact that we can write our potential energy function as a function of a single variable means that we'll be able to do an energy diagram. We can basically put R on the horizontal axis and energy on the vertical axis, and that's what our goal is going to be. All right, so what do we know about this force? Well, the force is 0 when separated by a large distance, or when R is large, because R is the distance between them. So by convention, and we can always do this, we can always fix a particular value of the potential energy wherever we want. We let U go to 0 as R goes to infinity. So by the way, the point I'm making is that maybe we would have had maybe we would have had that limit as R goes to infinity of U of R be 6 joules. So all I'm doing is I'm taking U of R, whatever it was, and subtracting off 6 joules from it, because you can always add or subtract a constant to a potential. So I'm just making it so that, so the constant I'm choosing is the constant such that the potential energy when R is very large goes to 0. All this does is it basically grounds us on our axis, right? We could have chosen, when we were doing the gravitational potential energy, we could have chosen mgy plus 6 joules, right? And that would have shifted our whole graph upwards by 6 units. So by selecting, but the fact that we selected the constant 0 here instead of 6 basically told us something about the, it's not quite related to Newton's law of gravitation. The fact that we chose a constant of 0 here told us basically where our graph is going to be, where our horizontal axis is relative to our graph. And the same is going to be true here. Basically, this just gives us a reference point to work with. So another fact about this Lennard-Jones potential is that the force is strongly repulsive when the particles are close. I.e., one way to think about this effect is that think of them as being two hard balls. If they get too close, they'll bounce off each other because they can't pass through each other. So there's a very strong repulsive effect if they get too close. Also, we have above a certain separation, the force becomes attractive. But it peters out as r goes to infinity. And that has to be true because we know the force is 0 when r is large. What's r? Lowercase r is just the distance between the two particles that we're modeling. And then the last statement, the last qualitative feature of the Lennard-Jones potential is that when particles are within a certain range of distances from each other, so I'll write it this way, when, well, no, I'll write it in words. When the particles, I haven't told you what it is. There just is a place when the particles are close to each other, i.e. say from 0 to some small value where it's strongly repulsive. When particles are within a certain range of distances from each other, everything in today's lecture is fair game. From each other and their energy, their total energy, is not too high. I know that I'm using qualitative language here, but that's kind of the point. They behave as if they're separated by a spring. Everything in this lecture is fair game. Wednesday is not included on the exam. By the way, I hope you guys remember I did mention that I'll probably have to go over today. So if you can't stick around, that's fine. I will be recording this as usual, and I won't cut off the recording until I'm done. I know not all of you guys can afford to stay, but we do have to cover enough material. I'm trying, and I can talk about the review session and all of that business afterwards, but I have a lot of material to get through. So I'm not going to be answering exam questions today. All right, so now the goal is to just draw a plot of this function. So let's put energy up here, separation distance over here, r, and let's try to draw this. So, okay, so we know, so let's first try to grasp these concepts. So the force is 0 when r is large. Well, what does that mean? Well, the force, we know that the force is the derivative of it's the negative derivative of the potential energy. So we know that the slope of this graph, whatever this graph is, should be 0 or should approach 0 as r goes to infinity. So we should have a flat bit. Maybe it's sloping down or it's sloping up, but there should be something approaching flat as r gets large. And similarly, we also know that, or we choose the convention, that the potential energy goes to 0 as r goes to infinity. So what we could have is we could have either something sloping up or something sloping down. Those are two possibilities for large values of r. By the way, r can't be negative. So I'm actually going to erase that negative side because r is a distance. It doesn't make sense to talk about negative distance. And so I'm actually going to make this bigger so we can see a little bit better. And pardon my fat R and E. So we either have something sloping down or something sloping up. But regardless, you can't have something sloping down approaching 0 from below. So we know that this is what the tail end of our potential energy function should look like. Now we know the force is strongly repulsive when particles are close. So what does that mean? Well, repulsive means that the force acts to make the distance larger, right? You have two objects. If they're repelled, the force will push on them to make the distance larger. So we should have a force that points to the right, because a force going to the right indicates that R is getting larger. And so if R gets larger, that means they're getting repelled from each other and so on. So what kind of force, what kind of slope for this function do we need to have in order to have a repulsive force? Well, we know that positive slopes correspond with force to the left, and negative slopes correspond with forces to the right. And that's just because the force is negative du dr in this case. So if we want a repulsive force, that means that we should have a negative slope. And if the force is very strong, that means the slope should be very large. So what we're looking at is close to the left, we're looking at some sort of large slope going downwards. And we know that that slope should get very high as they get closer and closer to each other, and it should, well, it has to go down because it's a force to the right. We also know that above a certain separation, so say, let's just call that certain separation, say, R0 here, the force becomes attractive. So that means that we have to have some sort of force like this. Attractive means that the force points to the left, which means a positive slope. So let's just put that there. And then we have that between, when the particles are within a certain range of distances from each other, and that their total energy is not too high, maybe even consider total energy is, maybe consider there is zero kinetic energy, we have that they behave as if they're separated by a spring. So what's the potential energy shape for a spring? It's a parabola. So we know that in some region, this is in the region where, well, let me back up. So in some region, we have a parabola. Now, where should that region be? Well, we know that when they're very, very close to each other, you have a repulsive force. When they're when they're above a certain separation, you have an attractive force. So the natural choice to place this would be somewhere here. So the whole point is that when we're using these qualitative features, we're trying to connect these features in a continuous way. And so what we end up with is something that looks like the following. Oh, and by the way, I didn't mention any other equilibria. So we're not missing anything. This should be all there is. So let me rearrange this to make something a little bit more continuous. So here we have all of the features. We have highly repulsive when they're close to each other, i.e. when their value is smaller than some value of R0. That repulsive factor gets smaller and smaller, and when you're close enough to the bottom of the parabola, it behaves like a spring. That checks out. When you're above a certain separation, you get an attractive effect, but that attractive effect peters out as the distances get larger and larger. And in fact, this is the general shape of the Lennard-Jones potential. Basically, it just tells you that you have that two molecules, or two atoms, or whatever, two particles, can't overlap each other because they have a strong repulsive effect. But they'll just sit there and oscillate nicely if they don't have enough energy to go very far. They'll just oscillate as if they were attracted by springs. And then if you give them enough energy, say if E total was here, then it's possible for them to escape off to infinity. This Lennard-Jones potential has an explicit formula for it. I'm not going to go over it, but the idea, this is just to infuse into your brains this idea of the Lennard-Jones potential, because it'll come up again. And hopefully you can see how we assembled this, this shape just from these qualitative features. All right, now I have to change gears completely. So I'm going to open up a new, come on, do the thing, a new page. And we're going to talk about impulse and momentum. I'd love to stop and ask questions, but we're just rough. Basically, if the potential energy function looks like a parabola, then the particles behave like a spring, behave like they're pulled together by it. Like, if the potential energy looks like a parabola, then the potential energy behaves like an elastic potential energy in that region. All right, so we have some terms to define. So impulse, we first have to discuss what impulse is. So if two objects collide, what do they have in common? Well, this might seem like a weird question, but if we want to come up with more physical principles, this is a reasonable question to ask. We know that if two objects collide, one is going to push on the other, right? But by Newton's third law, the other is going to push back on the first with equal and opposite magnitude. So that tells us that the magnitude of the force from 1 on 2 is equal in magnitude and opposite in direction to the force from 2 on 1. Right, so this is a statement of Newton's third law. We also know that the time in which the force is applied from 1 on 2 is the same as the time in which the force is applied from 2 on 1. Basically, for the duration that they are in contact and applying these forces, those times are the same, right? Because they're both touching each other. So what that means is we can define a quantity called impulse. And that quantity, J, is equal to the magnitude, it's equal to some force times some duration. So this is the same for both in a collision. And these are third law pairs. And so, which implies, so what does this imply? This implies that the impulse from 1 on 2 is equal, sorry, the magnitude of the impulse from 1 on 2 is equal to the magnitude of the impulse from 2 on 1. So right away, it looks like that this impulse idea might be useful because it's a quantity that's the same for colliding. That's the same for for both of the two objects in a collision. So I'm going to put another header here, momentum, and I'll explain why in a minute. But let's first talk about the difference between work and momentum. Sorry, work and impulse. So first, delta T is the same for both. It's the same for both objects in a collision. So work is a scalar, right? It's just a number, 5 joules, 18 joules, -6 joules, and impulse is a vector. We use the letter capital J, by the way, for impulse. Don't ask why, it's just what we do. The magnitude of the impulse doesn't care about the direction of the force, right? You could have, if you have a force and you apply that force in a direction that it's perpendicular to, like let's say you have gravity pulling down, but the object's moving left or right, the value of the work will be different depending on what direction the force is applied, right? Because there's a dot product involved. So if the force and the path are perpendicular, you get 0. If they're not, you get non-zero. However, the impulse is just the impulse. It doesn't matter what direction the force is applied. You can always compute the impulse. Third, work doesn't have a third law equivalent. We talked about this before. But impulse does have a third law equivalent. Right, because the forces have a third law and the duration of contact, well, of course that's the same, then of course the impulse has a third law. So, and the point here is that because the forces are equal and opposite in Newton's third law, the impulses are also equal and opposite. So why do we care about impulse? And how do we use this? So it turns out that just like how work can tell us about mechanical energy, this is the energy associated with potential energy or kinetic energies, impulse can tell us about mechanical something. And we'll figure out what that is. But let me give a quick example. let's talk about books sliding. Remember that example where we had one book sliding on top of another book? So we have A is sliding on top of B. So let's draw a free body diagram for A. So a free body diagram for A would look something like this. There's a frictional force being applied to the bottom of it, right? And so the impulse, and there's also going to be gravity and there's a normal force, but we're going to ignore that for now. We're just looking at the frictional force. The impulse delivered to A can be easily computed. It's just the force, which is negative F in the I direction, times the duration of the magnet, the duration of contact. So the impulse, JA, is negative F delta T in the I hat direction. This is schematic for now, but it'll get more clear in a minute. Now let's look at the free body diagram for book B. So book B is going to have a frictional force of equal and opposite magnitude pointing to it or pointing to the right on it. And so we can compute the impulse delivered to B. So all we're considering right now is just one block starts with motion, the other block starts at rest, and they're just sliding together. This is a collision. So the impulse delivered to B is just F. Well, it's the force. In this, it's the same magnitude of the force because it's a third law pair. This time it points to the right, and it has the same duration, delta T, in the I hat direction. So what do we find? We find that JA plus JB is 0. That shouldn't be so surprising, but maybe it is, right? If you add these two things together, you get the 0 vector, the vector with 0 magnitude. So what does that tell us? It tells us that the force on A times delta T plus the force on B times delta T is 0. And from Newton's second law, we get that the mass of A times the acceleration of A times delta T plus the mass of B times the acceleration of B times delta T equals 0. Oh no, oh okay, there it is. But what is the acceleration? Now, we're going to assume that this is a constant acceleration problem, but all of this is valid if we just turn all of the deltas into Ds. Like if we take delta T and make it a dt, it's equally valid. But for our sake, let's just consider just deltas. Well, acceleration then is just delta VA over delta T times delta T plus MB times delta VB delta T times delta T. That's still equal to 0. And so what we get is we get MA times delta VA dividing through by, or canceling out the DTs, plus MB delta VB. That's equal to 0. And now we're going to assume that the mass of the objects is fixed. It's a reasonable assumption. The books aren't gaining or losing mass. And so what that tells us is that we have delta of MA VA plus MB VB is equal to 0. And this MA times VA plus MB times VB, that is that's the mass of MA plus B times the velocity of MA plus B. And what I mean by this is the MV of the system. So at least in this simple example, we see a new conserved quantity, because a conserved quantity is just something that doesn't change, not considered. Deltas act just like derivatives when you take product rules. So for example, if I had a derivative here, and it was an MV MAVA plus MBVB, that would be the derivative of M, but that's not changing. So this is MA times dVA dt. Basically, it behaves precisely like a product rule. I'm not going to go into a whole lot of detail, but it makes sense, right? If you computed the initial value here, and you computed the final value, that would be the same as if you had computed this. Just consider this as final minus initial, and then all of these things make sense. And the masses don't change. It's basically just a regrouping of the final minus of all of the finals together and all of the initials together. So we have a new conserved quantity here, and it's not energy. And we call this, or this conserved quantity is the product of mass and velocity. We call it momentum. Which is abbreviated or written as the vector p. Because of course it's a vector, velocity is a vector, and you can multiply velocity, you can multiply a vector by a number and still get a vector out. And so what we write then is we have that, by definition, come on, right? Okay, there we go. So the definition here is that P is by definition mv. Oh, froze again. And P being a physical quantity has units. By the way, when we put something in square brackets, we're asking what are the units of this thing? And it has units of mass times velocity, kilograms times meters per second. We don't really, there's no name for a momentum vector like there is for energy. Energy has joules, which is also kilograms meters squared per second squared. Sorry, kilograms meters squared per second squared. But momentum is just kilograms meters per second. So yes, the P. So above it is. So this thing here is the total momentum of this, or is the momentum of the system of the two books. Yes, that's precisely correct. So. So let's talk about momentum conservation then. I'm claiming that it's conserved. And at least in the example above, we showed that it was conserved because it doesn't change. Now, new conserved quantities are good, right? Like we liked conserved quantities. We liked introducing energy, or at least I hope you did, because what it did is it allows us to solve otherwise very hard problems, solve problems that we might not have been able to solve otherwise. And so anytime you have any sort of new conserved quantity, in our case momentum, you can hopefully use it to solve a problem that you wouldn't have known how to solve otherwise. And so let's try to think of what types of problems this might be useful for. Well, for energy, energy conservation was useful when we only knew information about the initial and final configuration of a system. Or maybe we knew information about the initial configuration, but we didn't know about the final. So the fact that we have momentum conservation, conservation means that there's a final and an initial. Momentum conservation also lets us solve before and after pictures or problems that have an initial and final configurations. So just like how with energy you didn't have to know what was happening between the initial and final conditions, as long as you have momentum conservation, you can still solve problems again without knowing things about what happens between the initial and final conditions. But by having momentum conservation, we now have a broader set of problems that we can solve, rather than just the ones that we could have solved with energy conservation. So just like how when we were talking about energy conservation, we talked about when energy is conserved, i.e. when there's no external work, we should probably answer the question, when is momentum conserved? Now, fortunately, it's basically the same time when energy is conserved. So for work, or for energy conservation, we needed no external work. So for momentum conservation, we need a closed system. Remember what a closed system is. It means that there's no external work or no external forces. And that's just like there was for energy conservation. You need a closed system for energy conservation as well. And so on top of this, on top of having a closed system, which means that there's no external work, we also need no external impulses. And one way to see this is just consider consider just Newton's second law, right? And I'll get to this more explicitly in a bit, but consider Newton's second law. If you just have a single body, well, if you have some external impulse, or if you have some external force, then and that force is applied for a duration, then there is an external impulse. And so this is to say, F equals ma for just a single body. Well, that means that F delta t equals ma delta t. And the whole point is that if this is not zero, then the acceleration isn't zero. And so if the acceleration isn't zero, then the momentum of course is going to change, because that means that the velocity is going to change. And so if the velocity changes, then the momentum changes. So you cannot have any external impulses. And indeed, you can't really have any external forces either, because if you have an external force, then you have an external impulse. But I'll get more into that in a minute. I just want to state for you guys the impulse momentum theorem. We had a work energy theorem. The impulse momentum theorem is basically the momentum equivalent, which just says J external impulse is equal to the external force times delta t, which is equal to delta of p, the change in momentum, which is just delta mv. So the impulse tells you, or external impulse tells you how much the momentum changes by. That is, if the momentum of a system is conserved, if there are no net external impulses on the system. I say net because you can have two external impulses that cancel each other out. So let me get back to that point I was making before on a single object. So, come on. There we go. So let's say that we have some external impulse. We're going to apply the impulse momentum theorem. That means that that's equal to, by the impulse momentum theorem, delta mv, which implies we can divide through by delta t, that we have F external is equal to m times delta v over delta t. And that's just equal to m times a, assuming that the deltas are small enough and everything's constant and so on. So the point is the impulse momentum theorem is exactly equivalent to Newton's second law. So if Newton's second law is true, which we just showed that they're equivalent, if Newton's second law is true, then the impulse momentum theorem should be true. So it should not be surprising that the impulse momentum theorem holds. Just a quick note about momentum and how it's different from work. You can't dissipate momentum. So you can dissipate energy with thermal energy, right? Like you can take mechanical energy and convert it to thermal energy, and then you're not getting that energy back. But there is no equivalent to thermal energy for momentum. There is no quote unquote thermal momentum. So the point here is that you should make very, very special care to keep kinetic energy and momentum separate. Like they are separate things. Kinetic energy can be dissipated to thermal energy, momentum cannot. So keep them separate so that you can make sure that you're applying the right principles in the right places. So what's the final conclusion there? Or then, how do we decide when momentum is conserved? So when is momentum conserved? Well, let me write this out so you guys have it in writing. We ask if all the forces involved are internal forces to the system, that is. Maybe ask that all forces involved are internal to the system. That makes more sense. The point is if there are external forces, then you might not have momentum conservation. But if all of the forces in your system are internal, well, then you will probably have total momentum conservation of your system. Just like if there are no net forces on an object, then the object has no acceleration. Similarly, if there are no net forces on a system, then that system will have no acceleration, meaning that there will be no change in momentum. Now, there is this whole business of partial momentum conservation, and I just want to briefly gloss over this. So what does it mean for a vector to be conserved? I kind of have swept that under the rug until now. It kind of makes sense for a number to be conserved. It just means that that number doesn't change. And so when we say a vector is conserved, what we mean is that all the components of that vector don't change. Or, let's use better English, are unchanging. So if a vector is conserved, like momentum is, it means that the x component, the y component, and the z component of that momentum, they all have deltas that are 0. Like the delta px is 0, delta py is 0, and delta pz is 0. However, there are more specialized cases where only one of the components is not changing, right? So for example, let's say that an object is falling, right? An object, or better example, let's say you throw a ball, right? Assume no air resistance and so on and so forth. Once the ball is in motion, there's only one force acting on it, right? There's only gravity, and that acts in the downward direction. So because there's no external impulses on the ball that you've thrown in the horizontal direction, that means that the horizontal component of the momentum is unchanging, because we know that the impulses affect the impulse directly changes the momentum. So if the x component of the impulse is 0, then the x component of the change in the momentum is also 0, which means that the x component of the momentum doesn't change. So we can have partial momentum conservation when we have no external impulses in the direction that we're interested in. So we have momentum conservation in the horizontal direction when you throw a ball, because there's only gravity pointing downward, whereas you don't have momentum conservation in the vertical direction. So that's just a tidbit. You can still use momentum conservation even in cases where there is an external impulse, as long as you know what direction that external impulse is in. You can, in some lucky cases, you'll be able to apply that to the other directions, the momentum conservation. Now, before we move on, I do have even more new material to introduce, unfortunately. I have to introduce this idea of center of mass. And I promise that all of this will come together today. We might just have to go a little bit over. I'll combine all of these ideas and we'll be able to solve some real problems, and I'll show you what it looks like. So momentum works really well when there are only internal forces, right? Let me write that down. That's a good sentence. Like, it's very useful for us. Like, we can, if there are only internal forces, then we know a lot about what happens to the velocity, for example, because the momentum is conserved. And so you can use the fact that mvf minus mvi is 0, or something akin to that. So let's look at an example. So let's say that we have a block, say of mass m1, connected to another block by a spring of mass m2. Right? So let's suppose that initially the blocks were connected to each other, but the spring was really tightly wound, right? It was compressed. And they're at rest, so you're just holding them there, waiting to let them go. So V1 is 0 and V2 is 0. Well, after you let them go, what happens? Well, Oh, by the way, let's also assume that they're actually not connected, that like that they're just kind of pushing on it, but if you let them go, they'll be released. The spring's just there to provide some sort of repulsive force. After we have V1 goes, or mass 1 goes out, you have the spring being nice and uncompressed, and then you have mass 2 goes out in the other direction, right? I mean, your intuition should agree that that's what happens. And in this case, there are no external forces. If you consider the two masses and the spring to be your system, there are no external impulses because there are no external forces. I think maybe you just put these on a table so they can slide. So what does that mean? It means that the momentum of the whole system is conserved, right? No external impulses means that the momentum of the system doesn't change. So before, our momentum was M1, or let me write PI. This was M1 V1I plus M2 V2I, I for initial. That was our initial momentum, right? It's just the sum of the momentum of the momenta of the components. And after, we have PF is M1 V1F plus M2 V2F. And so momentum conservation tells us that PI should be equal to PF. But PI is 0, right? The velocities of both blocks is initially 0. So the momentum is just 0. The system has no momentum initially. And it froze again. Maybe once I get my stimulus check, I'll buy a new tablet. So what do we have? We have that 0 equals PF. Oh, froze again. And so we can actually use this equation to solve for information about the blocks. We can rearrange this equation to get that the velocity of the first block is equal to negative M2 divided by M1 times V2F. So if, for example, the second block is a lot heavier than the first block, then that means that M2 divided by M1 is a lot greater than 0. Sorry, a lot greater than 1, like maybe it's 100 or something, which would mean that the magnitude, the speed of the block, of the first block is a lot higher than the speed of the second block. And that should agree with your intuition. A good example of this would be a semi-truck hitting a Prius, right? If a semi-truck is going 60 miles an hour and it collides in the opposite direction with a Prius going 60 miles an hour, the semi-truck's not going to change speed a whole lot. The Prius will completely reverse direction. So momentum conservation basically, or one consequence of momentum conservation, is that lighter objects will be affected more in collisions than heavier objects. This, by the way, is an example of a collision. You have two objects interacting and then they're bouncing off each other. This is a simplified collision, but it is a collision. And so from just that alone, we didn't have to know anything about the spring. We can learn stuff about the velocity of one of the blocks given the velocity of the other block. Now, recall that momentum conservation comes about thanks to Newton's laws, right? It basically comes from Newton's second law. And so let's return to Newton's second law and consider these two blocks as a single system. So what is the net force on the system? Well, there are no external forces, so it's 0, precisely. So systems with 0 net force, we know that they experience 0 acceleration. The system experiences 0 acceleration. Now, that might seem counterintuitive to you guys because clearly these blocks accelerate away. So the question then is what went wrong? Well, if you think back to like the first week, I brought up this business of the center of mass, or the acceleration of the center of mass, and that's really what's happening here. Newton's second law refers to the acceleration of the center of mass of your system. No net force means we can use momentum conservation. Yes. Newton's second law refers to the acceleration, the A in F equals ma, the acceleration of the center of mass of the system. So I didn't actually explain what the center of mass was at the time, and I promised I'd get to it, so we're getting to it. So let's, in order to define this, let's work with the example we have. Let's rewrite the momentum conservation to see how center of mass is defined. So momentum conservation that we have is 0 equals m1 v1f, and I'm going to drop the vector symbols because we're working in one dimension right now, but for the most part, everything holds for vectors as well. So our momentum conservation equation looks like this in the x direction. So that is, well, what is the velocity? The velocity is just the change in position over time. And so the velocity for block 1 is the change in position of block 1 over time, and similarly for block 2. And so if you guys notice, this is just the derivative of m1 x1 plus m2 x2, right? You can factor out a derivative, and because the masses don't change, this is totally valid. So that says that 0 is equal to, and I'm going to multiply and divide by something, 0 is equal to m1 plus m2 times the time derivative of m1 x1 plus m2 x2 divided by m1 plus m2. I multiplied and divided by m1 plus m2 just to get it into the form that I wanted it to be in. So this is equal to, this m1 plus m2 on the outside is m total. That's just the total mass of the system. Hopefully you guys agree with me there. And then this thing is defined to be the center of mass, or the x position, the position in the x direction of the center of mass. So this is equal to the time derivative of x sub cm, or it's just m total times the velocity of the center of mass. And that's defined to be p total. Right. All I did was I wrote out what the total momentum is. So if all of these equalities are true, then we're good. Everything tracks. So this whole business of multiplying and dividing by m1 and m2, and then combining all of the x1s and m's and all that business, this gives us a formula that we can use for the center of mass of more than just 2 points. So remember that r is the displacement. It's basically the position vector of an object. So the center of mass position vector, the location of the center of mass, for a collection of objects of different masses is m1 times r1. So the mass of the first object times the position vector of the first object, plus m2 times r2, the mass of the second object times the position vector of the second object, plus m3 times r3, and so on, divided by m1 plus m2 plus m3, and so on. That is our general formula to get the position of the center of mass. And so if you want to look at the position in the x direction, the center of mass in the x direction is m1, m1 times x1 plus m2 times x2, and so on and so forth, divided by m1 plus m2 plus ... And then you can do the same thing for the center of mass, the position of the center of mass in the vertical direction, m1 times y1 plus m2 times y2 plus ... divided by m1 plus m2 plus so on. The point is what we're doing is we're basically doing a weighted average of position. What do I mean by that? What I mean is that, like, if you want to find the center of mass of an object, you guys might have an intuition for that, right? Like, the center of mass of this phone is in the middle, because you have the same amount of mass on the left as you do on the right. And so the center of mass basically tells you at what place do you have the same amount on either side? Do you have the same amount of mass? And so if you have, for example, if you have like a mass of 2m here and a mass of 1m here, you'd expect the center of mass to be twice as close to this one as it is to this one, right? Because you have twice as much mass over there. So the center of mass isn't quite just the average of the positions, but it's the average of the positions after you weight their positions with their mass. So the more mass they have, the more they contribute to the average. So that's what I mean when I say a weighted average of position. So the center of mass isn't just a position, though. We've also mentioned a center of mass velocity, and in fact, you can go as far as to say the center of mass, to talk about a center of mass acceleration. So in the spring box system above, we saw before that the velocity of the center of mass was 0 initially, and the velocity of the center of mass must be 0 afterwards as well, by momentum conservation. And so in general, what we have F external, so the external forces is equal to the time rate of change of the center of mass momentum with respect to t. And this is just MACM. This is just mass times the center of mass acceleration. Maybe another 15 minutes or so. I wanted to get to an example. I was hoping to talk about the elastic collisions, but I'll try to go quick and not keep you over too much. But if you do have to leave, feel free. And again, this is being recorded. So the center of mass acceleration, well, that's just the time derivative, the second time derivative of the center of mass position, just like you would normally do just like you would normally do for just a single object. This is m1 times the second derivative of r1 dt squared plus m2 d squared r2 dt squared plus dot 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 divided by m1 plus m2 plus dot dot dot. And that can be simplified to just m1 times a1 plus m2 times a2 plus dot 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 divided by m1 plus m2 plus dot dot dot. So the point here is that once we know something about the center of mass acceleration, for example, in this simple example, the center of mass acceleration is 0 because there's no external forces, we can then use that to actually compute the acceleration in the various directions. So before I start giving examples, it's useful to talk about a very special reference frame. Oh no, where'd it go? Oh no, where'd it go? So this special reference frame, remember I was talking about reference frames before when we were talking about relative motion, is the center of mass frame. The idea here is that sometimes a complicated system can be simplified by just looking at what happens in the center of mass frame of that system, using the position and velocity of the center of mass, calling those things 0. Like, for example, just like how we can say that from the reference frame of a person on the train, their velocity is 0, we can say that from the center of mass reference frame of an object that's moving, its center of mass is not moving. Of course, that's tautological. So an example of this center of mass business is an exploding projectile. The center of mass frame, why it's useful, is an exploding projectile. So let me just give a quick summary of this. Let's say you have a hemisphere connected by a spring to another hemisphere, and let's say it's launched at some velocity, at some angle, right? So, and then maybe when it gets to the top of its arc, it separates. And then this half goes, say, here. The center of mass does something. And then this half goes here. So maybe we measured this value, call it R1. I don't know why it keeps minimizing. Can we use that to figure out where the other one landed? The answer is yes. So what you would do is you would first figure out where you would find the location of the center of mass using the range finding equation. You'd find this position using the range finding equation from whenever. Just assume that the center of mass is not moving, or is not, sorry, how do I want to phrase that? This is like a projectile, so we know that there's that momentum is conserved horizontally. So the range finding equation should work for to find the horizontal position of our projectile, or the horizontal position of the center of mass of our projectile. And then we can solve for R2 by knowing where R1 is. And that's just using this definition of the center of mass. I'm not going to go into detail there. It's relatively straightforward. You just treat the whole thing as if it were moving as a single body, and it lands at the center of mass. And then you can figure out the unknown value by using the definition of center of mass and the known value. All right, so one more thing to talk about, and then we'll call it, so maybe another 10 minutes or so. So we have this whole business of center of mass, we have momentum conservation, we have impulse. We can now combine everything together to be able to solve otherwise very hard problems. So we're going to combine momentum and energy. We're going to use both conservation tools in order to solve complicated problems. So let's look at that example again, where we have a mass connected or attached by a spring to another mass, but maybe they have different masses now. And so before they're connected, the spring is compressed. Come on, drag. Ah, there we go. There we go. So before we have that, in the aftermath, we have M1 is speeding away that way. You have your spring being uncompressed, and then you have M2, or 2M, sorry, speeding away that way. So initially, the spring has some potential energy, right? So we can use that fact to analyze this problem. So first, note that the kinetic energy of an object is equal to 1/2 mv squared. You guys know that. But that's equal to 1/2 times m squared v squared divided by m, which is just 1/2 times m times v quantity squared divided by m, which is just p squared divided by 2m. So another way to write kinetic energy is the square of the momentum divided by 2m. Yeah, it'll probably be another 5 or 10 minutes. So because momentum is conserved in this example, the two blocks have to have the same magnitude of momentum, right? In order for, there's only two things that have momentum. The total momentum is 0. So if they're going in opposite directions, the thing going left has to have the same magnitude of momentum as the thing going right, and then you just add them together to get 0. So what we have is that the magnitude of P1 is equal to the magnitude of P2 in the final case. Initially, neither has any momentum. So what does that imply? It implies that P1 quantity squared is equal to, and I'm actually going to write this just as the way that we typically would, P1 squared. This implies the vector P1 dotted with itself is equal to the vector P2 dotted with itself. And so if the momenta squared are equal to each other, then we can just write down the kinetic energy of each one. Kinetic energy of the first object is P1 squared divided by 2m1, which is just P squared divided by 2m. I'm just going to label this P squared since they have the same P squared. And Ke2 is equal to P2 squared divided by 2m2, which is P squared divided by 4m because it has twice the mass. So this is precisely equal to half the kinetic energy of the first block, right? And so what we can do then is we can say, look, if the spring had this much of a spring constant and it was compressed this much, maybe we already knew that, then we know what the total energy of the system is. There's no initial kinetic energy. There is some initial potential energy, and all of that energy has to go into kinetic energy at the end. And so the fact that we now have a relationship between the final kinetic energies of each of the two blocks, and we have a relationship between their momenta, and we know what the total energy and the total momentum is, that will let us solve for velocities explicitly. So I think I'm going to, I don't want to start talking about elastic collisions now. Actually, I'll just briefly summarize what an elastic collision is. So a collision is just any two objects that interact with each other, right? And those are the only two forces. So the nature of the force between the two objects, however they're colliding, maybe they're just bumping into each other, or maybe there's a spring between them and they bump into the spring and then bounce off. Whatever type of force that is, doesn't actually really matter. Yes, yeah, we're assuming no external forces here, no external forces at all. And there's no non-conservative forces internally either. Like, it doesn't matter if it's a spring or just two objects bouncing off each other. The internal force or the nature of the force doesn't matter, because we don't need to know what's actually happening between before and after. We just need to know what's before and what's after. However, depending on what the force is, it could be the case that the internal forces might change the thermal energy of the system. So, for example, think of those two blocks sliding. Some of that kinetic energy is lost because it's converted to thermal energy. So if the collision force is quote unquote springy, for example, like two balls being or two blocks being bouncing off a spring, or maybe two billiard balls colliding, we say that then you can say that the force is conservative, or at least nearly conservative. And we call collisions where the collision is springy, we call those elastic collisions. They behave similarly as if there was a spring between them. If the collision is frictional in nature, like two blocks sliding together, then we call those forces, or then the force is non-conservative, and we call those inelastic collisions, INELASTIC. And so the whole point is that for elastic collisions, and by the way, I'm going to go over this in a lot more detail on Wednesday, but for elastic collisions, we can use both momentum conservation, which always holds regardless of the type of force, assuming there's no external forces, and we can use energy conservation because there are no non-conservative forces. We can assume the mechanical energy is conserved. For inelastic collisions, we still have momentum conservation, but we don't necessarily have energy conservation because some of that energy is lost to friction. So basically, whereas momentum conservation effectively gives us somewhere between 1 and 3 equations. All of this stuff gives us somewhere between 1 and 3 equation constraints, like mvx equals mvx, mvy equals mvy. Basically, all of those, the momenta in each of the 3 directions is conserved. If a collision is elastic, meaning it's a springy type of collision, then we get a 4th conservation, or a 4th equation to use. We get energy conservation. Total energy, or the change in total energy is 0. Whereas we might not get that for inelastic collisions. All right, so that's all I'm going to say on elastic collisions and inelastic collisions for today. I'll cover it in more detail on Wednesday, but I'm not going to have elastic collisions and non-elastic collisions on the exam.